Hello everyone. Today inshallah we will continue on the parametric representation of certain functions. I'm really very happy to be with you today, and hopefully today's lecture is not going to be long, it's going to be a short one, and also it contains a valuable information. It's not hard to follow up with, and of course we will continue after our short break inshallah. I want you to remember what we did go through in the previous lectures. We already did go through various types of conics and quadratics, also through the coordinate systems, various coordinate systems, either from polar in 2 dimension or spherical, cylindrical in the 3 dimension. In the previous lecture, we already did go through functions and several variables, and we represented, in some cases, the parametric representation, how to get attention to plan, and so on. Today we will continue on this. This is one of the problems on your workbook. I've tried to send it to you, and I believe it's in sheet 4, not 3, sheet 4. And I've sent all of this to you through WhatsApp, and you will find, of course, everything on Moodle. For this problem, he is asking you to determine the vector equation of a tangent. So we back again to the vector equations of a tangent to a certain curve. But here the vector equation of the tangent line to the curve x equal to theta minus theta and y equal 1 minus cosine theta at the point corresponding to theta equal to pi over 4. As you can see, here the parametric equation is given in, or the equation of this curve is given in parametric form. So the first step in order to do this and to get this straight line equation, which is the tangent equation, I will have to have r, which represents the position vector, and once you substitute in it, it will give you the tip at this vector, which is the point that you will need. And also we can differentiate this position vector and getting the vector of the tangent line at that point. This is what we are going to do exactly. So if we try to represent x equal to theta minus sine theta and y equal 1 minus cosine theta, so remark. If I try to work with theta starting from 0, so once you insert to 0, this is going to be a 0 minus sine 0, which means the x coordinate will be 0. Also in a similar manner, 1 minus cosine 0, which has come up to 0, and this is the main point. Increasing the values will give an x and y. It's like trajectories as in the definition previously. And so you will have the shape as you can see for this function. Now I can write r, the position vector, which consists of the x component of this curve times I, the unit vector in the x direction, plus 1 minus cosine theta, which is y in the j direction. Once you have r, substituting with theta equal to pi over 4, will develop directly the point that you will need in order to get your line. So just substituting with pi over 4, and this equation, this is going to be pi over 4. This is going to be a sine of pi over 4, which is 1 over root 2, as you know, from the right angle triangle with angles pi over 4. So as you know already, this is pi over 4, that's pi over 4, so it's going to be 1, 1, and root 2. From this triangle, we can get all the values of the sine and the cosine. Now, I have the value of this vector, position vector, which is pi over 4 minus 1 over root 2, 1 minus 1 over root 2 in the direction of j or the direction of the other x. Now, if I differentiated this one, I will get the slope of the straight line. And I can represent the equation successfully in parametric representation, which has been defined previously, is on the equation as the equation of a straight line equal to the point which I have at the time being, plus some constant which is lambda times the vector of this straight line. Now I will get this vector. So all I have to do is to differentiate this equation and get our direction vector. So start differentiating. Differentiate theta, which is going to be 1. Sine theta, which is going to be differentiated to be cosine theta. خليك معايا يا يوسف. Then cosine theta, start to differentiate, is going to be minus of a negative sine theta. So it's going to be 1 minus cos theta in the direction of I plus sine theta in the direction of j. In a similar manner, using the substitution with theta pi over 4, I will have 1 minus cosine pi over 4, which is 1 over root 2, plus sine of pi over 4, which is also going to be 1 over 2. Now I'm ready to write the equation of a straight line, exactly like what I told you, which is the point plus lambda, direction vector, and where lambda belongs to r. All I have to do is to make this substitution happens and to collect the similar terms all together in the direction of I and in the direction of j. So simply, this is going to be the point, which is, as you can see, pi over 4 minus 1 over root 2, 1 minus root 2, then plus lambda times the coordinates of the vector will be here. Then we can stop at here, or we can get the I values all together and the j values all together. This is actually what happens here. These are the I components from the point and the vector, and these are the j's component also from the point and the vector. This is really very simple question, and we already did go through it in the previous lecture, so it's just like a recap as I told you. Now for lecture 5 and lecture 6, these are very interesting lectures. They contain a lot of information about how to make a parameterization of a function or of a curve in order to get the parametric representation of this curve in front of you. So it's really very simple just to go through it. Let's start about the definition of a curve and the tangent of a curve. So it's written that, let's see be the graph of a vector function r, differentiable at point t naught. Suppose that the r dash 2 doesn't equal to 0, so its derivative at this point doesn't equal to 0. It has initial point on the point of the vector rt naught. Then the vector rt naught is tangent to the graph, okay, of r, and points in the increasing direction of the parameter t. So if the parameter t is open as like this, as theta or something, it will be open in this direction. Now we have some definitions which is going to be important down the road. Hello. So the first of them, okay, come first. Okay, so the first definition, I'm really very happy to see you today. Is everything okay?
Everything's okay.
Okay, a vector function or a regular vector function is defined that R is a function of class C1. What's a class C1 function? It is continuous and differentiable. Okay, so it is continuous even on the first derivative. C1, and we write R dash equal to C1 with on the interval as a function on the interval on I if R dash is differentiable on I, and the derivative function is continuous in I. So if I write a function C2, it means the function by itself, the first and second derivatives are both continuous and differentiable. Okay? A vector function is said to be regular. This is another definition. It's said to be regular in its interval if R belongs to C1 and the R dash doesn't equal to 0. So the definition of a vector function or a regular vector function, there is two conditions: to be continuous, as you can see, and its first derivative doesn't equal to 0 at the indicated point. Now we will talk about regular curves, and if it is continuous, if it is closed curves or open curves. For a regular curve to be called regular, let's say be a curve on a line oriented in a space. Mainly we mean by regular curves the closed ones. Okay? So if C is a closed curve, what's a closed curve? That the initial point will overlap with the beginning point, the end point. And this is defined here. It is said that C is a simple curve if it has a single point of overlap. The initial point coincides with the endpoints. Like these graphs. See, here is C4 going to C3, going to C2, and then to C1. So it is a closed curve. All the lines are, or all the directions, one is beginning and the other is ending, and so on. And this is also another shape of a closed one. If C is not close to curve, C is said to be a curve. And it doesn't have an overlap. So something like this is the initial point and this is the end point. They are not coinciding with each other. Like this one, 2, this C1, C2, C3, and C4. This is the beginning and this is the end, and they are not connected. C is a regular curve. When we call, remark that we have regular vector functions as a definition, and we have regular curve. The regular curve, if it is simple curve, which means it's closed, and there exists a regular vector function whose graph is C. So, what we mean about a regular curve, that it has a regular function and it is closed one. Okay? Like an ellipse, like a circle, something like this. Okay, perfect. This is the exact definition. There is sectionally regular curves, which is a parametric curve C is said to be a sectionally regular if it is consists of some parts of it. All of them are regular parts. Number of regular curves C1 and C0, such that the initial point of Ci plus 1 is the terminal point of Ci, which means a curve that's starting and ending, and this end point is the new start for the common curve. Okay, so it's like those curves exactly. This is C1 start, the end point. The initial point. That's the end point of C1, which is gonna be the initial point of C2. The end point of C2 is gonna be the initial point, start point of C3, and so on. This is called sectionally regular curves. For parameterization of a curve in the plan or in the space, it's simply to describe this curve on a parametric form. This step is very important. If you are given the relation ready from start, half of the work is done, like the problem that we already did go through by the beginning of this lecture. And we will see how to change from Cartesian form of a function into the corresponding parametric form. We will go through this. So if you have a parametric description for a regular curve, so it's going to be R directed RV or RT, it's going to be f of t times I, g of t in the direction of j, and h of t in the direction of k. We already introduced this parametric definition previously in the last lecture, and we know the benefits of using a parametric representation, because once you use parametric representation, you are decreasing the number of variables in your equation. Either if you have like unknowns x, y, and z, a point, any point in 3 dimension will have 3 coordinates. So if you don't know that point, you will be missing how many variables? 3, x, y, and z. But if you have x as a parameter of t, y as a parameter of t, as a function of t, and z as a function of t, all these 3 variables will become just only one variable, which is t. Okay, the associated parametric curve could be x, y, z, f of t, g of t, h of t, and t belongs to the interval of this curve, and this is the parametric equations that expresses this equation. To convert a Cartesian, as I told you, to parametric form, number 1, identify the type of the curve. You have to identify your curve. So from our previous study in the previous chapters, we already know about what's the circle, which is the regular curve, what's the ellipse equation, the parabola, the hyperbola, some of the quadratics also. So you already know some of these equations. So first of all, start with different curves have different natural parameterization. Start with identifying your curve in order to identify what's the best equation that you will use. Number 2, introduce the parameter that will be your parametric unknown, like t or theta or something like this. Usually we take t, but there is no regulations on you. We usually take t for negative infinity up to infinity and theta for the angles from 0 to 2 pi or whatever the regulation, but it's not a rule. So sometimes we use sine t and so on. Famous shapes and equations and its parametric representation. Unfortunately for this part, you will have to memorize some of these equations. The good news is, for the famous ones, like the circle for example, you already know the equation of a circle. If I ask any one of you, Ya Yusuf, خليك معايا. Okay, so his spirit is around us in all times. He usually gets lost, but you know, we love Yusuf. So, the equation of a circle, which is going to be x squared plus y squared equal to a squared. Okay, so it's x squared plus y squared equal r squared, as I told you. Where are the radius of this circle? Remark that this is this circle. It's a center in the origin 0 and 0. Yes, so it is a function on the mean form. The good news that I was telling you about is it's like polar coordinates. So for the circle issue, the parametric equation will be directly r cosine theta plus r sine theta. If you have a complete round for theta, you will be able to draw your circle. So that's the parametric representation of a circle. And this is, you will have to memorize this. Okay, it's really very simple, not complicated at all. Remember, it is really exactly like the polar, okay, coordinates. Okay, what's the relation between polar coordinates and the relation between polar coordinates and Cartesian coordinates? That's x equal to r cosine theta, which is in front of you. So it's really very simple to connect them together. Okay, Ibrahim will ask me, this is the circle. In case the center is the origin, what if the center is not the origin? The other case or the general case of a circle. If you remark here for a general case of a circle, that's where the center is not the origin, the center is given by h and k. So for this case, all I have to do, just only to add h on x and k on y. So the new equation, or the parametric form, will be h plus r cosine theta, while y will be x plus r sine theta. So if you compare these two equations, all I did, Ibrahim, is adding the coordinates of the center beside, okay, the main two values for x and y. Okay, what's really very near to a circle? An ellipse. So the ellipse, the only difference is there is no one radius for an ellipse. You have two of them, a and b. So here's the equation of an ellipse: x squared over a squared, y squared over b squared. Okay, let's guess that. What do you think the difference will be? The difference in an ellipse, it's gonna be x equal to a cosine theta, b sine theta. So it's really very simple. And for the general case, it will be the same. Once more, this is the equation of an ellipse, x squared over a squared plus y squared over b squared. So once you try to parameterize it, getting its parametric form, it's going to be really, very simple. X equal to cosine theta, sine theta. This is supposed to be r in a time of a circle, but you have two radiuses, or radius. So this is a for the radius in the direction of x, and this is b for the direction of the y. If you have center other than the origin, which is the general case, all you have to do, exactly like the circles, adding h on the x component and the k on the y component, as you can see, which is very, very simple and testable. And also, if you connect it,
but that's if it's a horizontal.
this is the horizontal component
ellipse.
And the y component of an ellipse.
But there's a vertical component. We will switch the a and the b together.
For what?
If it's a vertical.
Yes, yes, yes. If you mean, my understanding, if you mean if the yes, exactly right. A here goes for the diameter that's beneath the x component, and the b goes for the diameter regardless of what's the big, what's the small. Here, the equation represents the radius that's beneath each one of them. Do you understand what I'm saying?
Yeah, I understand.
Okay, so first of all, you will have to put your equation on this form, in order to have a successful parametric representation. Some people will get lost understanding the ellipse shape and how x and y. Simply, all we have here is like this. This is the ellipse, and that's the x-axis, y-axis. This is the x-axis and y-axis. I'm talking about the general case first. And the definition of the parametric is, it's gonna make a trajectory for the x component and the y component. So if I went for this point, which belongs to an ellipse, I will get the x component from this dimension, and that's gonna be the y component from the other equation. Do you read what I'm saying? So mainly it's like trajectorying the points beside each other, okay? So these are the definitions for the ellipse equation. Those also, it's gonna be the equation for a parabola, y equal x squared. And in this case, this is simple, okay? All I have to do is to consider, other than the ellipse parabola, the circle, the ellipse, and the hyperbola. The hyperbola is very close to the ellipse, exactly like the difference between the minus sign. But in the hyperbola, and I will show it to you, we are not going to use the cosine term. It's going to be cosine. You will see it. But for the parabola, which is different, yes, which is different than the ellipse and the circle and away from the hyperbola a little bit, in such a case, I will choose one of these variables to equal to t, and the other one from the equation by itself, it will be represented. So, if I want to represent y equal x squared as a parametric representation, I can insert x equal to t, x equal to t, and then y will equal to t squared. So, I can consider x equal to t, and then from the substitution in this equation, y will be t squared. And it will run from negative infinity up to infinity. That's the parametric definition of parabola.
It's not so efficient when it's so, when the equation is simple. Because when it's
Yes.
complicated, it makes a lot more sense.
Yes.
Yeah.
Okay.
And
Exactly
it
right.
seems
Yes,
like
I
you switch that
understand.
to the X,
Yes, you are right. Okay, for x and y squared, it's going to be vice versa. You just insert y equal to t, and x will be t squared. If we go through, if we change it to lines, for example, I can insert x equal to t, and y will equal to mt plus c. That's the equation of the parametric representation of a line equation. Okay, if you have 2 points and you want to have an equation of a straight line, use the general formula that we used in 3 dimensions, which is take one of these points and get the difference or the vector between these 2 points. How to get the vector between 2 points? Getting the difference between the x values, y values, and z values, whatever. Here I'm in 2 dimensions, so I will get x2 minus x1, y2 minus y1, which is stand for the vector part, and I will use one of these points. So it could be x1, y1, then the difference in x times t, which is the parametric value, and the difference in y times t. This is the definition of x and t. General strategy for curves involving x squared, y squared, try to think about trigonometric forms like the ellipse, like the parabola, like the ellipse, like the circle. For lines, use a linear parameterization, x equal to t, and get y. For parabolas and other polynomials relations, express the variable in terms of t. Choose one of them, represented as a value of t, then the others will come from the definition of this equation with the shape of this function. It seems I have a problem with the batteries for my pen. Just a second. Just a second. Yeah. Okay. Now for a parabola opening upright, and this is the main definition of a parabola, if you remember. The h and the k are the vertex coordinates. And we usually go for the value of b, this is the lotus spectrum, if you remember, or the focal chord, which is 4b, So this value will be divided by b. If you did so, the definition of x is going to be h plus bt squared, and the y will be k plus 2bt. These need to be memorized. This is actually the a little bit complicated definition of dt from my point of view.
But that
For-
if it opens from the right or the left,
From the right or the left.
if up or down, we will switch the x with the y.
No. Yes, exactly right. By here from right to the left, depend on the sign of 4b, positive or negative. Okay, which is exactly right. For a parabola that opens upward or downward, the standard equation, exactly as you said, we will switch it in. We usually having a parabola which is symmetric about the x with no square. So if I have y equal x squared, it's going to be symmetric about the y-axis. If I have x squared equal y, y squared equal x, so it will be symmetric about the x-axis, okay? And also, that's the definition, the parametric definition of this parabola. This is what I'm telling you about. For a hyperbola, opening left and right the x-axis, so a normal shape of a hyperbola,
Without the negative sign.
the equation, yes, it's going to be exactly the same. I choose just, in order to simplify life, so I'm just to choose the general case of a hyperbola, which is x minus h to the power of 2 over a squared minus y minus k to the power of 2 over b squared. In this case, the funny issue is I will use cosine and sine. So it's exactly like circles, but instead of cosine, we will deal with cosine or cosine hyper with the same definition and everything. And also, this is the case if you have the switch. So instead of opening left and right, it's opening up and down. Okay? You remember this? Because we usually have a hyperbola, x squared over a squared minus y squared over b squared equal to 1. And in such a case, it will be to the left and right of the x-axis.
It would be like this.
If it was equal to negative 1 or y squared over b squared minus x squared over a squared equal to 1, in such a case, this is going to be the shape of this hyperbola.
You just switch the
Yes.
the x and the y.
Yes, exactly right. So it's going to be x equal to h plus b sine t and the k equal to a cosine t. These also, for a circle, let's go through some problems, some simple problems. Like, for example, let's represent x squared y squared equal to 4 in parametric form. Any ideas?
X equal
2
cosine.
cosine theta. And y is going to be 2 sine theta, or t, whatever. So it's going to be r cosine theta, r sine theta, that's the normal equation. Here we have r squared, which equal to 4. So instead, we will have r equal r to 2. So all my equation is going to be 2 cosine theta, y equal to sine theta, and theta run from 0 up to 2 pi. If you want to be sure that these coordinates will represent this equation, all I have to do is to make a resubstitution. So I will replace x with 2 cosine theta. I will replace y with 2 sine theta. Start making these substitutions in the left-hand side. You will end up having 4 fourths. This is a demonstration about this substitution. So instead of having x squared, it's going to be 2 cosine theta to the power of 2. Instead of having y squared, it's going to be 2 sine theta to the power of 2. So it's going to come up to 4 cosine squared, 4 sine squared. Take 4 as a common. You will have cosine squared plus sine squared, which is 1. And now it is proved. So for this, let's say, for this circle, which is the origin, is not the center.
X equals
So
3
first of all, yes, exactly right. The center is going to be 3 and negative 2. So for the x component, it's going to be 3, then plus a cosine, 5 cosine, t or theta, and exactly the same for the other component. It's going to be negative 2 and 5 sine theta. Here we go. Negative 2 plus 5 sine theta, and theta run from 0 to pi over 2. If I have something like this, which will end up having a hyperbola, because if you divide, there is a negative sign, and these values ensure that these semi diameters are not the same. So if you divide on 36, you will end up having this general form of a hyperbola, and so it's gonna be center 2 and the negative 1, a equal to 3 and b equal to 2, and it's gonna be 2 plus 3 sine t, y equal to negative 1, 2 sine t. But remember here, t is running from negative infinity to positive infinity. But in circles and ellipses, the theta will go from 0 up to 2 pi. Okay. For this equation, it's another hyperbola, but instead of having the x, this is going to be up and down. Okay. So it's exactly the same idea. X is going to be negative 3 and y is going to be positive 1. These are the coordinates of the new center. And for a, it's going to be, here a is not going to go for the, we usually, in the relations by the beginning of our course, we usually reserve the a for the bigger, or for the longer semi-ax. We call it the semi-major ax, okay? But with these equations, we are taking each value relative to the ax that's above it. So if I have y minus 1 divided by 16, I will consider a equal to 4. For the x, the b is going to be a 5, whatever, which is which. I hope this is not going to make a confusion or misunderstanding. So x is going to be a negative 3, which is the component. Since they are switched, so I will use shine, and I will have the semi-ax, which is 5, and exactly the same for the other part. This is also another example on parabola. This is the main equation. These are the parametric representations, but here I will have to have P, which is the part of a focal chord. So I will start with taking the 12, making it equal to 4P, so I will have the P, which is equal to 3. And starting from this, I can substitute it in this equation. Remark that the parametric representation of a parabola will depend on the value of P. So first of all, I have 12, it's going to equal to 4P, so P is going to come up to 3. That's exactly what's written here, P equal to 3. And then I will start substituting. This is the x component of the vertex, plus 3, which is P, T squared. And for the other guy, it's going to be 2P, which is 6 times T. And that's the y component of the vertex. It's exactly direct substitution. Also, for a vector on the other direction, I wanted to discuss this equation in depth and also show you that all the related substitutions. Please, I know this is simple and it needs memorization from you, but please, I will need you to rewrite all of this and resolve it again once more using your hand. Okay, for the quadratics, I will usually use a free substitution. But in general, like the regular curves, like regular similar curves like ellipsoid, for example, I will use the spherical coordinates. This is why we did go through spherical. Okay, Ibrahim? So, in order to describe this quadratic, which is in 3 dimension, it's of course, you know from the equation, it's an ellipsoid. Okay? Because the semi-axes are not equal, so it's an ellipsoid, okay? So, all I have to do is to use the spherical coordinates, if you remember. The spherical coordinates goes for z equals c sine theta, but you add m, which is the coordinates at the z, which is similar to what we did with the ellipse and the circle. And this is our cosine theta, sine phi, cosine theta, cosine phi. Theta here stands for the angle of the z-axis, and the phi stands for the angle that goes from 0 up to 2 pi. So that's the definition of theta, from 0 up to pi, or from negative pi over 2 to pi over 2. That one goes from 0 to 2 pi. That's a direct example on the ellipsoid. Here I have the center, which is 2, negative 1, and 3. Remember that we take the numbers with the opposite sign. So if it is positive, I will go for the negative value, okay? And for the semi radiuses, it's going to be 3, 2, and 4, and try to arrange them the way you like. then we will make just a direct substitution in the spherical coordinate change. I will do these couple of examples and I will stop and we will continue in the next lecture, inshallah. Okay, here he is asking you to consider the line C in R2 defined by the equation which is x minus 1 to the power of 2 plus 1 minus 2 to the power of 2 equal to 3, which is, that's an equation of circle, which means x will equal to the root of this value, which is going to be root 3. So x is going to equal to 1 plus root 3 cosine theta, and y will be 2 times sine, root 3, sine theta. So here's the r, which is root 3, and that's the k, which is going to be 2. These are the center and the radius. That's the representation of the circle. Here is asking you to give 2 points in space P and Q, determine a parameterization of the segment PQ. And this is exactly what we did in the beginning of this lecture. I will get the point, any point of them, plus lambda and the vector connecting these 2 points. How to get the vector PQ? I will get the difference between the Q coordinates and the P coordinates. So first of all, this is the main equation of a straight line. Point plus a direction ratio times lambda, or T, okay, which is the parametric representation of the straight line in 3D. I will start with the direction vector.
That's the Cartesian form?
Yes, this is the parametric form. Okay. X, Y, and Z will equal these values in corresponding to a new variable, which is lambda, that belongs to R. Lambda, move this equation into the parametric plan. Okay. So now I will use this point, which is x naught, y naught, z naught, and then I will get x1 minus x naught, y1 minus y naught, z1 minus z naught. I will get the difference between these 2 points. Okay. Now I will take this q and that's p. That's the direction vector. All I have to do now for the parametric equation of this line is going to be x naught, the coordinate in the I direction, plus lambda times x1 minus x naught. This is the I component in the new line. And this is the J component, and that's the Z component. Okay? Here is asking you to consider oriented line C and R2.